Hi, so I thought I'd talk a little bit about charge controllers actually. Now, charge controllers seem to be immensely complicated, and I guess they are when you sort of get that black box and have a look at it and you start pondering what you can do with it. It's quite complicated. And it's like a computer. When you think about a computer, it's a complicated piece of equipment. But at the very basics of it, of course, it's actually really simple. All a computer is doing is turning a switch off and on. There's just a lot of them. And because there's so many of them, it gets quite complicated to look at it from the outside in. Now, it helps me when I'm trying to understand something to make comparisons between things, to give me links between things so that I can see where they came from, and also to have a bit of a look at the history of things so I can see how it developed. When I look at their thing in that way, then it helps me understand the mysterious black box in front of me that really is a huge book to read through to even learn how to turn it on. So that's what I thought I'd do. I thought I'd have a look at some of the basics of charge controllers, where they began and how they've developed, and then come up to charge controllers that we're currently looking at. So I've got a couple of bits of equipment here, and we're going to have a close-up of it. So what I've got here is a solenoid. It's a coil of wire. I'm going to put a current down. That creates a magnetic field, and in the centre there is a steel rod that'll get magnetised, and it'll be pulled into the centre of the solenoid. But this one I've attached to a rubber band. So it is a solenoid on a spring, and if I put some power in there, it jumps forward, take the power off, it springs back. Now, that might not seem mind-boggling to you. It is to me, because that is the basics of the very first charge controllers. They're electromechanical charge controllers. Now this one is just a solenoid, moves backwards and forwards. But if I put a switch here and attach the power to the switch, when the solenoid moves forward, it will turn the power off. As the power goes off, it springs back, which turns the power back on. So if you like, that's a way of sensing the power input and making sure that the spring setting won't go further than a previous voltage. Now that's exactly what I've set up here. So all we've got here is a solenoid. It's in a different arrangement. There's a circular coil here, the solenoid is a straight bar, there's a couple of magnets. So when I turn the power on, it will be pulled towards the magnet. And here I've got a couple of bits of metal that intersect the power. So as that pulls across, the power will get turned off, and then it'll go back. It will self-oscillate. It will self-oscillate at a certain rate. If I just left it by itself, then it would arc and go through a process called hunting. So what you do is across the coil, put a capacitor. The capacitor gets charged. It feeds it. When it breaks, the capacitor needs to discharge a little bit so it can stay broken, and then it will come back. So it prevents that hunting that we saw before. So let me set that up. Okay, it's connected to the power supply, and if I turn the power up, we can see it flickering backwards and forwards, shutting off. Now that's set at 5 volts. So it doesn't matter now what voltage I put in there, at 5 volts, that will turn off. So whatever the input is, the output is going to always be 5 volts. Now I can change that by changing spring tension, changing the position of the magnets, all that sort of stuff, but 5 volts is all that the output will be from that particular electromechanical device. So I actually think that's simple but really cool, because that stupid little electromechanical device there, the coil and the solenoid, what it does is it regulates the voltage. Doesn't matter what voltage I put in there. The only voltage I can get out is set by the spring tension, and in this one it's 5 volts. So that voltage will now never go above 5 volts. And in fact, this kind of voltage regulator here is what was used for a long time prior to creation of solid state. It was this kind of stuff. Now, these things actually still have use today for very high voltages. Of course they get more complicated, and of course we could use this particular version actually. Because we have a sweeping arm, we could sweep a series of contacts and we could get different voltages out of it, and that's exactly what happens when you do this but have a rotary arm, so you can get a rotation of step voltages using something like that. So that not only is a voltage regulator, it can be a variable voltage regulator just as easily. Now, for me, that's actually very cool. Now, why go about voltage regulation? Because, like I say, voltage regulation for me is the very basics of what charge controllers are all about. Charge controllers are all about making sure that you don't put too much voltage into your battery. Now, this is set at 5 volts because of the spring tension. Let's say I wanted to charge a lead-acid battery, I needed 14 volts. Well, I could change the spring tension so that it had 14 volts. And all of a sudden, I've got a battery charger with charge control. Now, I'm not suggesting people make something like this. What I'm saying is that this is doing a physical job in a way that we can see. The switch, if you like, at the end of here is being turned off. This, if you like, is sensing the voltage and making sure that the voltage is held at a constant. So this performs those functions of sensing and turning off the voltage supply that a simple battery charger actually does. Only that simple battery charger does it with some electronics, and this one is just doing it mechanically. But it's doing exactly the same thing. Now, because any voltage above that is basically just thrown away. What will happen is the coil will get hot. If we don't want that coil to get hot, we have to do something else with it. So I put a capacitor in series to prevent the hunting. If I put a light bulb in, then all the extra energy would go into the light bulb instead of heating this coil. If I put a large resistor in, all of that extra energy would go into heating the resistor, rather than heating and breaking this little mechanical device. And you will find charge controllers that do exactly that. They're called dump loads. They're a bit simpler, but they're exactly the same thing done electronically. What we actually have here done mechanically. What I've got here is a car alternator. Now, inside here is a little bit of solid-state circuitry, doing pretty much the same thing as that, because this will change the amount that it can generate depending on the speed of the engine. The faster the engine, the faster this turns, the more it generates, and you can get quite some voltage out of this. But of course, the main thing you do with an alternator is charge a battery. And if we put more than 14 volts into a lead-acid battery, we're quite likely to blow it up. So what the electronics does is controls the voltage in the same way that this did, to make sure that although the voltage here being generated can be quite high, the voltage that the battery gets is within that range set by this. This is set by, actually it's a diode and resistor series that set the voltage. Here we're using spring tension. We can use diodes and resistors to do that, but that doesn't really matter. It's setting the voltage so that the voltage is now independent of the voltage generated. So the voltage generated can rise up above, but the voltage the battery will see is only at the 14 volts. So this voltage regulator inside the alternator is in fact acting as a charge controller. And this is what I mean about these things being related to each other. Now, these aren't very efficient, obviously, because what we're doing with the excess voltage is essentially chucking it away. And of course, that's not great. And the other thing is, of course, it can have a very low voltage, and that low voltage isn't being used particularly efficiently, but the high voltage is chucked away. So the efficient performance of these isn't great. But it doesn't really matter so much in those applications, because you really just want to keep the battery topped up while you're running around, and there's plenty of spare motion to do that, so it's not an issue particularly. It becomes an issue when you're using things where you need to get every scrap of power out of there and save it. So things like photovoltaics and wind turbines, we don't want to be really chucking that energy away. I mean, there are occasions when you do, like if you're charging and you're saving it to your battery bank, then once your battery bank is full, you don't want to be charging it anymore, so you want to chuck it away. And that's part of what the charge controller will do. So when we're looking at voltage regulation, we don't have that extra little bit that's going to be needed to pay attention to what happens at over voltage and, if you like, under voltage too. Okay, that's pretty much enough for one video, I think, because it's already getting a bit long. And the main takeaway here is we're looking at voltage regulation leading to battery charging. And what's happening in voltage regulation is a specific set of functions. It's got a logic to it. The logic's really simple. Provide a voltage. If there's too much voltage, turn it off. Those logical things are implemented with specific methods of doing it. Now, we used a mechanical method because you can see it doing it. This is sensing the voltage. Once the voltage goes above, it's turning the voltage off. It's performing those logical blocks, but in a mechanical way. Of course, now we do it with electronics and solid state, and we'll be looking at that and where that's developed and why that's developed in the next couple of videos. But all I really want you to get hold of here is that there is a simple function being performed. That function is a logic. The logic can be implemented in many physical ways. As long as you get that in your head, what those functions are, then it should demystify the whole thing a little bit. And of course we're going to be looking at those kind of block diagrams and how it is implemented in solid state later. Anyway, I hope you enjoyed the video. I hope it begins to make a little bit of sense, and thank you very much for watching.